just to briefly identify a little bit more about this with optical activity. Because of the structures of enantiomers, they only differ in the same way your right hand differs from the left. They have the same physical properties, but enantiomers differ because they interact with their chiral compounds differently, and they have optical activity. They will bend plane polarized light in a very, very unique way. Only chiral compounds are optically active. So that's going to be something that we talk about in the next section. Why? Well, it's because of some really unique characteristic with the actual tetrahedral structure of the R and how it differs from the tetrahedral structure of the S orientation, that the actual stereoisomers and enantiomers have different biological effects on our bodies. Biggest one, we talked about this earlier, at least hinted to it, the idea of L versus D amino acids. L amino acids, which are the R notation, they are used by the cells to produce proteins. They are the amino acids that we actually can use, and therefore they can rotate plane polarized light in clockwise, counterclockwise rotation called lever rotation. But what's really important to know is the D amino acids, the same structure, just the mirror image of it, is actually not used in our bodies at all. It occurs in the cell wall of bacteria, though, and it rotates plane polarized light in the opposite way, clockwise. And so we'll see that these ideas of chiral centers are extremely important, even though it might be something that, well, it's the same molecule, right? No, they're not. Drug design is extremely important for us and our society today. And if we did not have a good grasp of chirality, there would be no way that we could actually truly understand how the drug would work in our bodies. Yeah. Hopefully that one's not lost. Pause, stare at it for a while. Thank you. This is the point where I'm just going to bring up one little bit in section 5. We talked about enantiomers a lot, so hopefully we'll digest that. These are non-superimposable mirror images, right? So we can label these R versus S when they are in a structure. Now, a diastereomer is the other compound that we want to be able to talk about. I just want to present one because we've already seen it. A diastereomer, by definition, is going to be a non-superimposable, not mirror image. That can be R's and S's. We'll get there in a little bit. The one that I want to give you right now is that cis and trans idea. So cis and trans, they're not mirror images, but they're definitely not superimposable, and it's their orientation that's different. So cis and trans stereoisomers are in the diastereomer category. Diastereomers will have completely different physical properties. So that's just something that we're going to really hone in on a little bit. Just wanted to get that other idea here, that we have enantiomers, which are mirror images, non-superimposable, but diastereomers are where our cis and trans stereoisomers fit into our big picture. Okay, optical activity. Enantiomers, like we've talked about a lot so far, have R and S configurations, and they can rotate plane polarized light in opposite ways. This is a basic idea of the electromagnetic spectrum, that there is an electric field and a magnetic field, and they are perpendicular to each other. Now, when we get that light and we can make it plane polarized, this is normal light, where it's going out in all directions. I'm going to label light as HVs coming up. Now, when we polarize it, what happens is that direction becomes one direction, no pun intended. There is a specific rotation that can happen. And so if light passes through the slit that matches, right? See how this matches in terms of the direction of the light, we can see it and it can pass through. If we decided to rotate, right, and only let that specific light pass through that is perpendicular, no light would actually pass through because we polarized it. Only compounds that can rotate plane polarized light are called optically active. Only compounds that are chiral are optically active. So if we ask you a question that says, is this compound chiral? Yes or no. We could also ask you, is this compound optically active? And that means, is it chiral? Same idea. Now, how do we measure this? It's with a polarimeter. Now, polarimeter tests, has a light source, and it has a polarized filter on it that's fixed. And you put your sample in here, this long tube. Now you know the amount of sample that you have, the concentration, you know the path length. It's kind of like a fancy spectrophotometer here, but you, the observer, are actually going to be analyzing the sample rotation. And so what happens is the sample, notice how this is all rotating the plane polarized light. It's taking that vertical light source and it's actually bending it. The arrows are actually changing, and there's a degree, whether it's to the right or to the left, that can be analyzed. You have an observation ocular device that you can look through and then rotate and come up with a actual degree. We won't be dealing with that. What we want to actually deal with is the idea that enantiomers will rotate the plane of light to equal degrees, but in opposite directions. So we'll use the positive and negative signs to determine what specific rotation we observe. Now, if you were in the lab, you might observe a specific angle. This is the concentration of your sample, because it is concentration dependent, and this is the path length of your sample cell. It's also dependent. Now, we will mainly be giving you the specific rotations, but I wanted to make sure that you knew how they actually were calculated. An observed angle will be in a degree. The concentration is usually in grams per milliliter. And then the path length is usually 1 decimeter, 10 centimeters, but it usually is in the decimeter unit. And that is what we call a specific rotation. Normally, it is reported in a specific rotation in a textbook, or it could be reported to you on a table with a temperature and wavelength. So the wavelength is based off of what light source. Normally, it's sodium or deuterium, some sort of a light source is used. That will tell you the wavelength. And then also the temperature. This is temperature dependent. And so changing the temperature actually can change the specific rotation. This is a crazy cool phenomenon. This is how they're usually going to be reported in alpha D20s, right? And so when we look at these two enantiomers of 2-bromobutane, we see that there is a chiral center. Take a minute, quickly identify whether it's R or S. Pause the video. This one should be R. This one should be S. An alpha D20 for a pair of enantiomers is exactly the same, just opposite in sign. So to tell you whether it rotates to the right or to the left. Now the plus and minus sign is what tells you if it's to the right or to the left. So we'll get there in just a second. But notice how the R for this one is a negative 23.1 degrees and the S is a positive 23.1 degrees. That tells you that these are enantiomers. The positive rotation is called dextrorotatory. And so what that means is that is to the clockwise, counterclockwise rotation, or to the right if you're thinking about clockwise, how a clock goes. Levorotatory is counterclockwise. And the negative. Now, when we think about positives and negatives, we can think clockwise, right? Or counterclockwise, left. But notice this compound below. This guy has the S configuration. That doesn't mean, just by noting R and S, that doesn't tell you if it's positive or negative. You actually have to go into the lab and figure it out. So there's no correlation between R and S and positive and negative. So do not assume that. This one's a unique compound because its optical rotation is negative at 20 degrees, but it's positive at 100. So thinking about that, do not correlate R and S with positives or negatives. You actually have to go into the lab to view optical activity. The magnitude and direction of the optical rotation cannot be predicted either. Has to be experimental. Think about this as kind of like your rate laws of general chemistry, when we said you have to have experimental data. We can predict the rotation of one specific thing, just like Louis Pasteur kind of noted for us, and that historical story was important because he noticed that with a 50-50 mixture of two enantiomers, that is what we are going to call a racemic mixture. So if we had these two compounds together, let's pretend that we had a 50-50 mixture. This mixture would be optically inactive because half of the compounds were rotating in the negative 23.1 degrees, and half of the compounds are rotating back to the positive 23.1 degrees. So a racemic mixture is a perfect 50-50 mixture of enantiomers, and it is optically inactive. What we can do is if we're trying to make this molecule and we're trying to see how much R and how much S do we have, we can use a polarimeter to quickly identify what the specific rotation was and compare it to the textbook specific rotation. And that's what's truly important about optical activity. For unequal amounts of enantiomers, the enantiomeric excess, the percent EE, can be determined from the optical rotation observed in the lab. So what you would do is if you were trying to make 2-bromobutane and you wanted to see how much R and how much S you actually made, you would take your sample at the end of the day and stick it in a polarimeter. If you had an observed alpha, if you had an observed specific rotation, then you don't have a 50-50 mixture. You have one enantiomer that is in excess. And so what you can do is you can actually use this percent EE to calculate the actual amount of R and amount of S. So let's just have a quick example. The observed alpha is negative 4.6 degrees. What does that mean for the percent EE? And what is the percent of R and the percent of S in the mixture? Think about that as a percent yield, right? There's the big old question. So quickly, couple of things that we first want to identify. Which compound, R or S, is in excess? Who do we have more of? We have more of the R because that negative tells us it matches with the observed specific rotation. Excellent. So when we're looking at this percent EE, we're going to take the absolute value, but I want to make sure that we're looking at that and saying, okay, if the absolute value divided by the absolute value of the pure enantiomer, what can we say about this times 100%? That is a 20% EE. There is 20% more R than S. How did I know R was excess? Because of the negatives matching. If we had an observed alpha of positive 4.6, then we'd have more S than R, because the S in this case is positive for S2-bromobutane. Now, for a percent yield, be very, very careful. I need to figure out what that percent EE means. Here's what we're going to do. We're going to take that 20% and add it to what's left over divided by 2. This will tell me the actual percentage of R in the structure, or in the compound, in the mixture. So why did I subtract 20 from 100? 80% of my mixture is racemic. What does that mean? 80% of my mixture is optically inactive. Half of that mixture is R, half of that mixture is S. So 60% should be R, 40%, 100 minus 60, is S. That is the actual percent yield. We will practice this. This is a big amount of math, and it's probably the only amount of math that we're ever going to do in this semester. All right, looking back again, the idea of enantiomers and diastereomers, we're going to see that enantiomers are those non-superimposable mirror images. Diastereomers are the stereoisomers that are not superimposable and not mirror images. We saw this was the first idea of this was the cis and trans stereoisomers exist here, but there's more, right? So cis and trans stereoisomers, looking at the double bonds, right? Those ideas, those stereoisomers are specifically diastereomers. They're not mirror images. There's no way you could rotate them or find out that they're mirror images. They are non-superimposable though, right? Their connectivity is different, is the same, but their orientation of those connections is different. Diastereomers have different physical properties. Cis-butene is more reactive than trans-butene. Trans-butene is more stable because those big groups are on opposite sides of each other. Now, when we get big cyclohexane groups, when we get lots of substituents on molecules, when we get more than one chiral center, that's where we get the diastereomer, and we're going to practice this a lot. But what's really important to note is that when you have 3 substituents on a cyclohexane, and all 3 of those carbons in cyclohexane are chiral, there are 8 possible stereoisomers. Holy cow. Notice the enantiomers, right? These are enantiomers, and so are these ones, where all 3 chiral centers are opposites. We could find the mirror images of these if we drew them all out in the chair conformations. Go for it if you really want to. But you split up and you go to a different pair, that's a diastereomer. That's a diastereomer, that's a diastereomer, that's a diastereomer, that's a diastereomer. Diastereomers are all the other relationships that we have. What's really important to note is that there are only 2 molecules that can be a pair of enantiomers. If you have more than one chiral center, 2 chiral centers or more, right? If the chiral centers are exactly opposite, that is the enantiomer. If one stays the same and one is different, that's a diastereomer. Now here's the rule. For the number of possible stereoisomers to be determined, we look at the number of chiral centers, 2 to the n, n being the number of chiral centers. So if you have 1 chiral center, 2 to the 1 is 2. There are 2 possible stereoisomers. They're going to be enantiomers. There's no diastereomers. That's the simplest way. But if you have two chiral centers, 2 to the 2 is 4. You're going to have 2 pairs of twins. You're going to have 2 pairs of enantiomers, and everybody else will be the diastereomer. Here's cholesterol. How many? 1, 2, 3, 4, 5, 6, 7, 8. Yikes. Yeah, there are a lot of possibilities for stereoisomers. And guess what? Cholesterol is the one that works in our body. So crazy. Any compound with one chiral center will be a chiral compound. With more than one chiral compound, it may or may not be chiral. Here's where I was hinting towards a new word. And I just want to present these guys again from the very beginning of our lecture. This versus this. Now we can categorize these. Are these enantiomers or are they diastereomers? Well, notice that they have both the wedge methyl on the top and a dash on the one and a wedge on the second for the bottom carbon. They would be diastereomers, but let's look at this compound a little bit more closely. The trans isomer is chiral. It's optically active. This cis isomer is achiral, not because it's specifically cis, but it actually has a plane of symmetry in it. What's really important to understand is when we have a plane of symmetry, I wanted to draw it here in these projections so you can see it. You can also see it in the skeletal structure. That plane of symmetry, I call this the taco. Think about folding it in half like a taco shell. That plane of symmetry creates an achiral molecule. Think about this trans. This trans guide, there is no symmetry. And that's because one of the methyls is wedged and one of them is dashed. Now, the cis isomer will have a plane of symmetry when the substituents are identical and cis, right? So this with 2 methyls is symmetry. Same thing here. Cis, 2 identical groups. Where's the symmetry? Right there. We gotta practice finding this symmetry because that means that this compound is achiral. Same with the other one. The 1,2 dimethyl is the same as, is achiral, and so is the 1,3 dimethyl when they're cis. Molecules with an even number of chiral centers that have a plane of symmetry are called meso compounds. Another way to test if it's a meso compound is to see if it's identical to its mirror image. So let's bring up that cis 1,2 dimethyl again, right? We said it had a plane of symmetry, right? There are an even number of chiral centers. Now, let's imagine drawing the mirror image or drawing the enantiomer, right? I'm going to draw the mirror image. And then what I really want to do here is one of the beauties of the iPad. I'm just going to rotate this and look, it's superimposable. The mirror image should be the enantiomer, but these are not enantiomers. They are identical. That is truly what a meso compound means. Be very careful with these. We're going to practice with all the planes of symmetry and being able to do that. But if you have an iPad or if you're just writing this on a piece of paper, cut this out. Do some crafts, right? See that being able to rotate. Again, rotating the molecule like this, just spinning around kind of like a lazy Susan if you are vintage like I am. You know what that is. That ability is really important. Drawing a molecule or having a molecule kit is great. Drawing it, cutting it out, rotating, flipping, doing all sorts of things so that you manipulate the structure is extremely important. But if a compound has a plane of symmetry, it's achiral. That's the main take-home message here. That means it is not chiral, not optically active, does not have an enantiomer. Its enantiomer is itself. So therefore, it's not an enantiomer, it's identical. Now, be very careful. We will avoid a lot of reflectional symmetry, but notice that through this inversion point, we can kind of see the idea of symmetry. This compound is an inversion symmetry, and so therefore this compound is achiral as well. The molecule does look like it has two chiral centers and no plane of symmetry, but it's still achiral because of inversion. Overall, the presence or absence of rotational symmetry is irrelevant to chiral. Rotational symmetry, right, being able to rotate things or flip things. What really is important is having a plane of symmetry within the molecule. That makes it a meso compound and therefore achiral. The only exception for the lack of plane of symmetry is the inversion center. And that's the only one I expect you to note. Okay, here's a couple other options for a meso compound. When we look at these meso compounds, what's important to note is where is the plane of symmetry and can we visualize it and notice things coming off are identical, right? It's kind of like having its own personal little mirror in there. Even this one right here doesn't have to be cyclic. Think of the taco. I relate a lot of things to food. Sorry. A meso compound also will have less than the predicted number of stereoisomers. Remember, because if you were to think about drawing all possible stereoisomers, the enantiomer is not different. These are equal to each other. So this is one of the options, right, for 2 to the n. That is not an enantiomer. These are identical. So usually meso compounds also have one less enantiomer or stereoisomer, excuse me, than based off of the 2n formula. Oh, chirality without chiral centers. We're going to talk about allenes mainly in class. Allenes are compounds that possess 2 adjacent double bonds. They may or may not be chiral depending on the substituents. So notice here, this carbon is sp hybridized. These two are sp2. Awesome. Okay. And the reason why the R groups are either in plane or wedged and dashed is because of the pi bonds. Now, remember that sp center has to have a pi bond on one X, Y, or Z, and the other pi bond has to be the opposite way, right? Perpendicular. And so these R groups are perpendicular to each other on opposite sides, right? So be very careful with allenes. The 2 groups on each end of the allene, if they are different, then the compound will be chiral. So if these 2 are different and these 2 are different, chiral. So quick example of allenes. If you want to draw them in a skeletal structure, this one would be achiral because on one side we have identical groups, right? Still an allene, just achiral. What about this one? Chiral. Nice. No R-ness denotions, no any way of identifying. You just can identify chiral versus achiral. The chiral one that I drew on the right-hand side, the ethyl is different than the methyl, and the methyl is different from the hydrogen. So that's why there's different groups there. Excellent. Now, I hinted toward this at the very beginning of this chapter. For some molecules, cis and trans for a carbon-carbon double bond is inappropriate. It doesn't work because cis and trans is only if you have one hydrogen on each carbon of the carbon-carbon double bond. You have to have at least one hydrogen, well, only one hydrogen on each of the carbon-carbon double bonds. If you do not have two hydrogens in the molecule, one on each side, then you can't use cis and trans. What you do have to use is the E and Z denotation. And that notation was developed around the same time as RNS, but it's from a German scientist, and so E and Z actually has a purpose. We'll get there in just a second. So what we're going to do is look at these two compounds. These are diastereomers because they are non-superimposable, non-mirror images, right? So what we can do is we can start to say, well, how would we actually name this? Which ones would be E and which one would be Z? We can't use cis and trans. We don't know what's on the same side or what's on opposite sides. Here's the process. Prioritize the groups on either side of the double bond. So smack dab, let's just draw a dividing line. And we'll say, who's higher priority? The ethyl, the carbon, let's call it carbon specifically. Carbon or fluorine. Fluorine is highlighted red there because fluorine gets priority over carbon because of atomic number. Isn't it nice when everyone works together and does the same prioritization? Atomic number. Now when we look on the opposite side, we have hydrogen versus nitrogen. Nitrogen is higher atomic number, so it gets priority. I usually put a little star next to these guys. And then I erase my dividing line and I say, awesome. I have my highest priorities on either side of the double bond. Now, once you have your highest priorities, then draw the line the other way, just like we did for cis and trans. And say, are the groups on the same side or are they on opposite sides? If they're on the same side, Z stands for zusammen, which means together. E stands for entgegen, which means opposite, German. So Lauren's famous German accent. If I ask you about the compounds and you say, Sie are on the same side, Sie on the same side. Z is German accent where, yeah, okay, cool. Moving on. E is just opposite side. If you remember Z, same side, then you'll remember Z is for together. And so we look at this first one where F and N are on the same side of that double bond. There is the Z. And where F and N are on opposite sides of that double bond, that's E. Nice. Let's just practice one more. I'll put this one in a ring structure. Okay, first thing that you do, draw a line separating the two sides. I'm going to go ahead and put in the hydrogen. I like to make sure I can see all of the things on each side of the double bond. And then I'm going to say on this top side, on this carbon right here, who's higher in priority, carbon or hydrogen? Carbon has the higher atomic number. Wonderful. Then I'm going to switch to the bottom, change color. On this carbon on the bottom, carbon or oxygen? Well, oxygen has the higher atomic number. Excellent. Now switch and draw a line so that you can see through the plane of the double bond. And are Z on Z same side? No, so it's E. Excellent. Thank you very much.